Okay, so we've got a little bonus video here for you in 157, and the point of this is going to be just to motivate this formula relating entropy to the heat and temperature. So we had that dq equals TdS, or ds equals dq over t, and so this had to do with, you had, say, a gas or some other system, and some heat flows in, and you want to know how much does the entropy change. Okay, so this was kind of one way we can think of this as just a definition of entropy. But then we had this other idea where entropy was somehow counting the number of microscopic configurations for a given set of parameters. So it's something like, if my system has a certain amount of energy E, how many ways can I arrange that energy? How can I give it to different molecules in different ways? And we said that the entropy was something like the logarithm of that number of ways. Okay, so what I'm going to do in this video is just to try to derive this equation, the ds equals dq over t, based on that microscopic picture. And we'll use a really simple model. So what I want to do is imagine that we have a certain number of molecules in my system, and I'm just going to think of these as some place where energy can go, some place that can store energy. So let's say I have k of these molecules, and I've sort of drawn them there just in a strip, just so we can easily visualize that there's a bunch of different locations where energy could be. And now I'm also going to simplify things by saying that we have some number of units of energy. We're imagining that energy is like a discrete thing, like the frogs in our analogy. So I have all these units of energy, like E, and I can place them onto the molecule. So any given molecule might have a certain number of units of these energy. Okay, so now our question is, say we have E total units of energy. I want to know how many configurations of there are for that number of total units of energy in my K molecules. All right, so this is kind of, it's just a math problem. It's a combinatorics problem. It's just counting all the number of ways, and it's pretty easy. If I had like 1 unit of energy and 3 molecules, then there are exactly 3 configurations. So I could just count them up, 1, 2, 3. But if I have a lot of molecules and a lot of units of energy, then we have to be a little bit more clever and use a little bit of combinatorics. Okay, so there's a nice trick for counting how many configurations there are. And the trick is, I am going to imagine drawing a significantly larger number of boxes. So I'm going to be drawing E plus K minus 1 boxes. And so the number of configurations with E units of energy in K boxes, okay, it turns out that that is equal to this this choose object. So it's the number of ways to choose K minus 1 things from E plus K minus 1 things. Okay, so how do I see that? Well, so I've drawn E plus K minus 1 boxes up there, And now I'm going to choose K minus 1 of the boxes. So, and I'll color them in black. So I'm choosing K minus 1 of those boxes. Okay. And so why is that useful? It's basically what I can do is think of those black boxes as dividers, where I started with, where I have E units of energy. Now those are the white boxes, the units of energy. Now I've put in all these dividers, and I've divided the system up into K parts. So I've put K minus 1 dividers, and so now I have the first part, and the second part, and the third part. Okay, and now you can see that for every way of choosing those black boxes from the total E plus K minus 1 boxes, then I can interpret that as a way of distributing energy between the different molecule boxes. And so in this example, I have 3 units of energy in the first molecule, 2 units of energy in the second, say 3, however many this is. Okay. And so that's just a math trick for counting how many kind of configurations like this are there with E total units of energy. Okay, so this is the answer to that mathematics question of how many ways are there to have K boxes and E total units of energy. Okay, and just if you don't remember the definition of this choose object, this is defined in terms of factorials. E plus K minus 1 factorial over K minus 1 factorial, and then the difference of the top and the bottom, which is E factorial. Okay, now if E and K are big numbers, which we're going to assume, then all of these factorials are really big numbers. Also, we're just going to ignore the 1 here. So this is E plus K factorial over K factorial times E factorial. Okay. Now the entropy is the logarithm of that number. So entropy is proportional to this guy and now we can use another mathematical trick, which is there's something called Stirling's formula, where the log of the factorial of a number is approximately equal to n times the log n minus n. Okay, and so we can use that here to say that this entropy is approximately equal to E plus K log of E plus K, and then minus E plus K, and then we have to, on the bottom, we get, so log with the K factorial on the bottom is like, it's like subtracting the log of K factorial, so we have to take minus K log K plus K, and then minus E logarithm of E plus E. Okay, so this is just all math, and we're going to simplify that. So that's going to give me E log E plus K log of E plus K. This cancels with these guys. Minus K log K minus E log E. And then I'm going to combine this term and this term, so that gives me E log of 1 plus K over E, and then plus K log E plus K log 1 plus K over E minus K log K. And I probably shouldn't, you can fast forward at this point. So then we can use the approximation that we're going to say that E is much greater than K. So we're just imagining that there's a lot of these, it's high enough energy that there's a lot of units of energy. We're not close to absolute zero, so each molecule has quite a bit of energy. And And then we can simplify this even further. So like log 1 plus x is approximately equal to x when x is small. Okay, so that first term, all of that is approximately equal to k. And then the second term is, I'll combine this term with this term, so that gives me plus k log e over k, and then that third term is approximately equal to k times k over e. Okay, so this term is k, this term is much smaller than k because e is much greater than k, and then this term is actually significantly bigger than k if we're imagining that e is a lot bigger than k. Okay. So in the end, the entropy overall is approximately equal to k times the log of e over k. All right. Okay, so if you weren't paying attention or you're fast forwarding, this is a good place to stop. And so let me just summarize. We have this simple model where we had k molecules, those are the boxes, and we had this e units of energy, and we wanted to calculate the entropy, which is just the number of possible ways to arrange those e units of energy. And so we've done some approximations. We finally got this answer that the entropy is like k times this log of e over k. All right, now let's imagine that we've got our system of molecules, and then we add a little bit of heat, which is basically saying we're just going to add a little bit more energy in there, and we want to know how does the entropy change. Okay, and so that dq, basically that's just going to take E, and now it's going to change it to E plus a little bit. Okay, which is equal to the dq. Okay, so how does the entropy change? Well, now we can just use a bit of calculus. So now it's just like taking the derivative or the differential here. So the change in entropy is going to be equal to k, which stays fixed, the number of molecules staying fixed. And then the log e, how does log e change? Well, the derivative of log e is 1 over e. So using the chain rule, we get ds equals k times 1 over e times our change in energy, which is going to be equal to dq. Okay. So what we finally got is now ds equals dq, and then that's divided by, I'm going to rearrange it to be E over K. Okay, so what is E over K? Well, this is like the energy per molecule. Okay, and remember, that was basically our definition of temperature. And so in the end, if we make that identification in our simple model, then we have motivated or derived with the right definition of temperature here this formula that ds equals dq over t. Okay, so that makes a basic connection between this definition of entropy, where it's counting the number of microscopic configurations, and then this other definition of entropy where we just define it to be equal to dq over t, which is the thing we're going to use in all of our calculations. And so that's pretty much all I wanted to say about that, and feel free to ask me questions if you have them.